Welcome to this problem walkthrough. Today, we'll be exploring problem number 1513, titled Number of Substrings with Only Ones. In this challenge, you'll learn how to count substrings in a binary string that consist entirely of the character 1. Let's dive in and break down the solution step by step. The problem is called Number of Substrings with Only Ones, and the task begins with a binary string S, which contains only the characters 0 and 1. A substring is simply a contiguous portion of the string, and our goal is to count how many of these substrings contain only the character 1. However, since the total count can become very large, we are required to return the result modulo 10 to the power of 9 plus 7. For the input, we are given a single binary string. The output should be an integer that represents the count of substrings with only 1, adjusted by the modulo constraint. To illustrate this problem, let's look at the first example where the input string is s equals 0110111. The output for this case is 9. Breaking it down, the substrings that contain only 1 include 6 single-character substrings, 1 at indices 1, 3, 4, 5, 6, and 7. Then, there are 2 two-character substrings, 11 at indices 4, 5, and 5, 6. Lastly, there is 1 3-character substring, 111 at indices 4, 5, 6. Adding these together gives a total of 6 plus 2 plus 1, which equals 9. In the second example, the input string is s equals 101 and the output is 2. Here, the substrings containing only 1 are much simpler. There are 2 instances of 1 as single characters, one at index 1 and another at index 3. Since there are no longer sequences of consecutive ones, the total count is just 2. In the third example, the input string is s equals 111111, which consists entirely of ones. The output for this case is 21. Let's break it down. There are 6 single-character substrings of 1. Then, there are 5 two-character substrings of 11, followed by 4 3-character substrings of 111, 3 substrings of 1111, 2 substrings of 11,111, and finally 1 substring of the entire string 111,111. When we sum these counts 6 plus 5 plus 4 plus 3 plus 2 plus 1, we get a total of 21. There are a few constraints and edge cases to consider. The length of the string can go up to 10 to the power of 5, and each character in the string is either 0 or 1. An edge case to note is when the string contains no ones, like s equals 0000. In this situation, the output is simply 0 because there are no substrings with 1. Conversely, if the string contains only ones, such as s equals 111111, the output becomes the sum of the first n natural numbers, where n is the string length. Another interesting scenario is when the string alternates between 0 and 1, like s equals 1010101. Here, each one is isolated, so the count is just the number of ones in the string. To solve problem number 1513, our goal is to count all substrings in the binary string that consist entirely of the character 1. First, we considered the brute force approach. The intuition here is straightforward: generate all possible substrings of the given string and check whether each substring contains only ones. For every valid substring, we simply increment a counter. However, implementing this requires iterating through all possible start and end indices to extract substrings, and then an additional check to verify if each substring is valid. This results in a time complexity of O(n cubed, in the worst case, making it inefficient for large strings. The space complexity is O(1), as we don't use any extra data structures. While this is a valid approach, the cubic complexity makes it impractical. Next, we evaluated an optimized sliding window approach. Here, the idea is to dynamically track substrings of ones by expanding the window when encountering 1 and resetting it when hitting 0. While this reduces the time complexity to O(n), the sliding window approach introduces unnecessary complexity for this specific problem, as there's a simpler solution available that avoids this overhead entirely. The third approach, and the one we ultimately selected, is based on a mathematical formula derived from observing the behavior of consecutive ones. The key insight is that a contiguous sequence of k1s contributes exactly k asterisk, k plus 1, / 2 substrings. For example, a sequence of 3 ones, like 111, contributes 6 substrings, 3 single-character substrings, 2 two-character substrings, and 1 3-character substring. This eliminates the need to generate substrings explicitly. To implement this, we traverse the string, keep track of the length of consecutive ones, and apply the formula for each sequence. This approach is optimal, with a time complexity of O(n), due to the single traversal, and a space complexity of O(1), as it doesn't require additional data structures. It's both efficient and simple to implement, making it an excellent choice for this problem. This method leverages the key observation that the problem can be reduced to summing contributions from sequences of consecutive ones, avoiding the need for nested loops or sliding windows. When comparing the approaches, the trade-offs become clear. The brute force solution, while simple to understand, is highly inefficient and impractical for larger inputs due to its cubic time complexity. The sliding window approach improves performance with a linear time complexity but introduces unnecessary complexity for this specific problem, as the task can be solved more elegantly. The mathematical formula approach stands out as the optimal solution. It combines simplicity, clarity, and efficiency, with a time complexity of O(n) and a space complexity of O(1). By reducing the problem to summing contributions from sequences of consecutive ones, it avoids the overhead seen in other approaches. This makes it the best choice for solving problem number 1513, as it provides an elegant and computationally efficient solution. The problem here is to count all substrings in a binary string that consist entirely of the character 1. For instance, if the input string is 011, 0111, the valid substrings include individual ones, pairs of consecutive ones, and longer streaks like 111. The goal is to compute the total count of such substrings efficiently. To achieve this, we use a greedy counting approach. The key insight is that consecutive ones in the string form groups, and the number of substrings that can be derived from such groups depends on their lengths. We begin by initializing a variable count to store the cumulative count and another variable current_ones to track the length of the current streak of ones. Additionally, to ensure that the result remains within the modular arithmetic limit, we define a constant mod with the value 10 to the power of 9 plus 7. With this setup, we can now iterate through the string to compute the result dynamically. As we traverse the string, if the current character is 1, we increment current_ones by 1, since the streak of ones continues. We then add the value of current_ones to count, which ensures that all substrings ending at the current character are included in the count. On the other hand, if the character is 0, it means the streak of ones has been broken, so we reset current_ones to 0. After processing the entire string, we return the result as count%mod to handle any overflow issues caused by the large number of substrings. This approach is efficient because it avoids the need to generate and examine each substring explicitly. Instead, it directly calculates the count based on the streak lengths as we move through the string. The greedy approach works because the number of substrings that can be formed from a streak of k consecutive ones is simply the sum of the first k natural numbers, which can be expressed as k*, k plus 1/2. However, instead of calculating this sum all at once, we incrementally add current_ones to count during the traversal, which is computationally faster. Using modular arithmetic ensures that the result remains manageable even when the input string is very large. For this algorithm, we only need two variables, count to store the cumulative total and current_ones to track the length of the current streak. This simplicity keeps the space complexity constant at O(1). The time complexity is O(n), where n is the length of the string, as we process each character exactly once. This makes the solution highly efficient. Edge cases, such as an empty string or a string with no ones, are also handled naturally, returning a count of 0. For strings that consist entirely of ones, the algorithm calculates the total substrings correctly using the formula for the sum of the first n natural numbers. For example, if the string is 111, the total substrings are 1 plus 2 plus 3 is equal to 6, and this is computed during the traversal. For mixed strings, where ones and zeros alternate, the algorithm resets current_ones whenever a 0 is encountered, accurately handling streaks of ones independently. The provided pseudocode implements this logic step by step. We initialize count and current_ones to 0, then iterate through the string. For each one, we increment current_ones, add it to count, and apply the modulo operation. For each 0, we reset current_ones. At the end, we return count as the final result. This approach ensures correctness across all scenarios, including edge cases. To understand the algorithm better, let's walk through an example where the input string is 011, 0111. Initially, both count and current_ones are set to 0. At index 0, the character is 0, so current_ones remains 0. At index 1, we encounter a 1, so current_ones is increment to 1, and count becomes 1. At index 2, another 1 increases current_ones to 2, adding 2 more to count, which is now 3. At index 3, a 0 resets current_ones to 0. At index 4, a 1 starts a new streak, incrementing current_ones to 1 and count to 4. At index 5, current_ones becomes 2, and count increases to 6. Finally, at index 6, current_ones becomes 3, and we add 3 more to count, resulting in a total of 9. Thus, the algorithm correctly computes the count of all substrings with only ones for the given input. This solution calculates the number of substrings consisting only of ones in a binary string efficiently. The algorithm uses a greedy approach, iterating through the string while maintaining a count of consecutive ones. Here's a detailed explanation. 1. Initialization. The variable mod is set to 10 to the power of 9 plus 7 is required by the problem to keep the result within the modulus. Count tracks the current streak of consecutive ones, while total accumulates the total number of valid substrings. 2. Iterating through the string, the loop processes each character in the string S. If the character is 1, we increment count, signifying the extension of the current streak. We then add count to total, which includes all substrings ending at the current position. 3. Resetting the streak. When a 0 is encountered, the streak is broken, so count is reset to 0. 4. Returning the result. After processing the string, the total is returned modulo mod to ensure it fits within the constraints of the problem. This approach is efficient with a time complexity of O(n), where n is the length of the string, as it processes each character exactly once. The space complexity is O(1), using only a few variables. This ensures the solution is optimal for large inputs. This is the Java implementation of LeetCode problem number 1513, number of substrings with only ones. The logic mirrors the Python solution, using a loop to traverse the string and calculate the total number of substrings containing only ones. Key differences include Java's use of explicit type declarations and modular arithmetic to handle overflow. The mod constant ensures the result is returned modulo 10 to the power of 9 plus 7. The solution is efficient with a time complexity of O(n), where n is the length of the string. To solve this problem, we start with the input string s equals 10101. First, we initialize a few variables. Mod is set to 10 to the power of 9 plus 7 to ensure we handle large numbers efficiently. Count is initialized to 0 to track the length of consecutive ones, and total is initialized to 0 to store the cumulative sum of substrings consisting only of ones. Now, as we iterate through the string, at index 0, we encounter the character 1. This means we increment count to 1, indicating the start of a sequence of ones. We add this to total, so total becomes 1. At index 1, the character is 0, which ends the current sequence of ones, so we reset count to 0. At index 2, we see another 1, so we increment count again to 1 and add it to total, making total equal to 2. At index 3, we encounter another 0, resetting count to 0. Finally, at index 4, we see a 1, increment count to 1, and add it to total, resulting in a total of 3 at the end of the iteration. After iterating through the string, the final calculation involves taking the total modulo mod. In this case, total is 3, so the result is 3%, 10 to the power of 9 plus 7, which equals 3. Now, consider a second example where the input string is s equals 111. Again, we initialize mod as 10 to the power of 9 plus 7, with count and total both set to 0. At index 0, the character is 1, so we increment count to 1 and add it to total, making total equal to 1. At index 1, we encounter another 1. Since this extends the sequence of ones, we increment count to 2 and add it to total, resulting in a total of 3. At index 2, there is yet another 1, so we increment count to 3 and add it to total. This brings the total to 6. The sequence of ones ends here, so we compute the final result by taking total modulo mod. In this case, 6%, 10 to the power of 9 plus 7, equals 6. In the third example, the input string is s equals 0, 0, 0. As before, we initialize mod to 10 to the power of 9 plus 7, and both count and total are set to 0. Now, while iterating through the string, at index 0, the character is 0, so count remains 0 since there are no ones to count. At index 1, the character is again 0, and count still remains 0. The same happens at index 2, where the character is yet another 0. Throughout the entire string, we do not encounter any ones, so total remains 0. At the end, we compute the final result as total %mod, which is 0%, 10 to the power of 9 plus 7, resulting in 0. The key to this solution lies in the incremental approach used to count substrings of ones. The count variable tracks the length of a sequence of consecutive ones. For every one encountered, we add all the substrings ending with that one to total. For example, a sequence of k consecutive ones contributes 1 plus 2 plus k equals k asterisk, k plus 1, / 2 substrings. By updating count and total incrementally, we avoid the need for nested loops, making the solution efficient. When a 0 is encountered, we reset count to 0 because substrings of ones cannot end with a 0. Finally, to handle large numbers and fit within constraints, we take the result modulo 10⁻9 plus 7. The time complexity of this solution is O(n), because we process each character in the string exactly once, and the space complexity is O(1), since we use only a few variables. In this solution, the time complexity revolves around processing the string s in a single pass using a for loop. For each character in the string, we either increment a counter count if the character is 1, or reset it to 0 if it's 0. The key operation inside the loop is updating the total variable by adding the current value of count. Let's break this down further. First, looping through the string involves iterating over all n characters, where n is the length of the string. This loop performs a constant number of operations for each character. Next, we have the operations of updating count and total. Incrementing or resetting the count variable, as well as adding count to total, are both O(1) operations. Since every operation within the loop executes in constant time, and the loop runs n times, the overall time complexity of the algorithm is O(n), where n is the length of the input string. When considering the best, average, and worst cases for time complexity, the results remain consistent. In the best case scenario, where all characters in the string are 0, the loop still processes each character and performs the same O(1) operations, leading to O(n) complexity. In the average case, where the string contains a mix of zeros and ones, the algorithm still processes each character individually, maintaining O(n) complexity. Finally, in the worst case, where all characters are 1, the loop again processes every character in the same manner, updating the counter in total as needed, which ensures the complexity remains O(n). Therefore, regardless of the input string's composition, the time complexity is consistently O(n). Now let's analyze the space complexity of this solution. The space complexity is determined by the amount of extra memory used, excluding the input string. First, the input string s itself has a size of O(n), but since it is provided as input and not additional memory, it doesn't contribute to the extra space usage. Next, we have the variables mod, count, and total, which are simple integers. These only require O(1) space, as their memory usage does not depend on the size of the input. Additionally, the algorithm doesn't use any extra data structures, nor does it involve recursion, which might otherwise increase space requirements. As a result, the total extra space required by this algorithm is O(1), making it very efficient in terms of memory usage. To better appreciate the efficiency of this solution, let's compare it with a brute force or naive approach. A naive approach would involve generating all possible substrings of the input string, checking if each substring contains only ones, and counting the valid substrings. This method would take O(n² time because it requires nested loops to generate substrings and perform checks. Additionally, it would require O(n) space for storing each substring being checked. In contrast, the optimized approach avoids generating substrings altogether. By leveraging the mathematical property of consecutive ones, it directly calculates the number of substrings ending at each one in constant time. For a sequence of k consecutive ones, the number of substrings is computed as k asterisk, k plus 1, / 2, which is an O1 operation. Since the algorithm processes all characters in a single pass, the overall time complexity is reduced to O(n), and the space complexity remains O1. This makes the optimized approach significantly faster and more memory efficient compared to the naive solution. When solving this problem, one common mistake is mishandling large substrings of ones. Many assume that a sequence of k consecutive ones has only k substrings, but the correct count is given by the formula k times k plus 1 divided by 2. For example, a sequence like 111 actually contains 6 substrings, not 3. Forgetting this formula can lead to underestimating the total count, especially for longer sequences. Another frequent error is ignoring edge cases where the input string contains no ones, such as 000. If this isn't explicitly handled, it can cause runtime errors when operations are performed on empty groups. Always validate the input and return 0 in such cases. Lastly, some solutions use inefficient approaches, like nested loops, which result in a time complexity of O(n squared). This becomes impractical for very large strings, so it's important to avoid these brute force methods. Another error to watch for is incorrect handling of modular arithmetic. If the problem requires results modulo a value like 10 to the power of 9 plus 7, forgetting to apply the modulo operation consistently during summation can cause overflow issues. The solution is to apply the modulo at every step of accumulation. Additionally, overcomplicating the logic for grouping ones can create unnecessary challenges. For instance, using complex data structures like lists of indices to track groups of ones adds overhead and increases the risk of logical errors. Instead, simple counters are sufficient and more efficient for this problem. A key insight for tackling this problem effectively is recognizing that consecutive sequences of ones can be treated as arithmetic progressions. Once you identify the lengths of these sequences, the formula k times k plus 1 divided by 2 can be applied directly to count all their substrings. Modular arithmetic is another important concept to master, as many variations of this problem require results modulo 10 to the power of 9 plus 7. Efficient iteration is critical to aim for single-pass solutions with O(n) complexity to demonstrate scalable code. Additionally, it's vital to prepare for edge cases, such as strings with no ones, strings that are entirely ones, or very long input strings. Robust handling of these scenarios is something interviewers often evaluate. Understanding and discussing related problems can also highlight your ability to connect concepts across challenges. There are several related problems that share similar concepts and can help reinforce your understanding. For instance, LeetCode 1524, number of subarrays with odd sum, also involves counting subarrays based on specific properties, which is a comparable skill. LeetCode 191, number of 1 bits, is a simpler problem that focuses on counting ones in a binary representation, offering a chance to practice bit manipulation. LeetCode 696, count binary substrings, emphasizes substring counting but focuses on substrings with equal numbers of zeros and ones. Finally, LeetCode 485, max consecutive ones, is excellent for practicing how to identify and process consecutive runs of ones. Exploring these problems can deepen your understanding and prepare you for variations in interviews. When considering alternative approaches, a sliding window method might come to mind, as it's often used for dynamic substring analysis. However, in this problem, it's unnecessary and can add extra complexity. Similarly, dynamic programming could be used to pre-compute substring counts, but again, this is overcomplicating what is essentially a straightforward task. The optimal strategy is direct iteration with grouping. Simply iterate through the string, compute the lengths of consecutive ones, and apply the formula directly. This approach is both efficient and easy to implement. The key insight here is that the problem boils down to efficiently identifying runs of ones and using a simple mathematical formula. Avoid the temptation to overcomplicate with advanced algorithms or data structures. Focus on clarity, correctness, and efficiency. Great job! To summarize, we tackled the problem by counting contiguous segments of ones and applying a mathematical formula to compute substrings efficiently. Remember, problems like this often appear in interviews, so practicing similar challenges will help sharpen your skills. Thanks for watching, and see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!